This one's about applications of circular functions. So we'll try to use a CAS a fair bit on this, but also try to complete a fair bit of this by hand. Let's see how we go. The height above ground X meters of a person at a ride at a carnival at time T seconds after the ride started moving can be modelled by this. How long in seconds does it take the ride to complete a revolution? Okay, so obviously like this is like the classic Ferris wheel question where like what we've got is like the Ferris wheel. It's a pretty basic looking Ferris wheel. But if we look at the person gets on here and moves around the Ferris wheel, it's exactly like a unit circle, okay? And so what that's going to produce is a function something like that, so a basic circular function. How long in seconds does the ride take to complete a revolution? So once around, well, that's just the period. So what we're going to do is note that it's a cosine function. So cosine has a period of 2 pi. And what we're going to do is divide it by our n value, which in this case is pi on 24. That is going to be 2 pi times 24 on pi, cancel, 48. Therefore, let's see what it is, X meters of a person, T seconds. So the time in this case is 48 seconds for a revolution. What is the height of the ride when T equals 20? Okay, so that's going to be X of 20 equals 6 multiplied by cosine. That's going to be 20 pi on 24 plus 6. Now 20 pi on 24 is, what's that? That's 5 pi on 6. Let's just check that, 20 on 24, 5 over 6. Yeah, it looks good to me. All right, so we want the value of cosine at 5 pi on 6, which is there, which is the same as the cosine of pi on 6. So that's going to be pi on 6 is root 3 on 2, and we want the negative version of that. So this is going to be 6 times negative root 3 on 2 plus 6 equals negative 6 root 3 on 2 plus 6 meters. All right, let's do this one on the calculator as well. So define f of x equals 6 times cosine, shift divide, shift pi, or shift 0 for pi, x on 24. Now, because I didn't use the variable x, I'm going to slap a multiply sign there, plus 6. All right, f of 20. Let's go into standard. What have they done there? They've simplified it a little bit, so we probably need to do that with our calculation as well. That's negative 3 root 3 on 2 plus, whoops, not on 2, negative 3 root 3 plus 6. Okay, that would be, as an approximation, 0.8 meters. So after 20 seconds, you'd be a bit less than a meter off the ground. Okay, so what I'm anticipating here, you get on the ride at like plus 6 or wherever it is, go around and you come back towards the ground, and then you just swing around and yeah. Write down the minimum and maximum heights reached. Well, if we imagine this function, what it's got is a mean line of 6. That means that it's raised 6 units up, and then an amplitude of 6. So the max height will be 6 plus 6, which is 12. So max is going to be 12, and our min is going to be 6. Take 12, which is 0. Right, let's sketch this. All right, so our period was 48. Okay, then we're going to divide that by 4, which is 12. Okay, we want it for the first 120 seconds. So 12, 24, 36, 48, 60, 72, 84, 96, 108, 120. Okay, it's got a mean line of 6, so we're going to go 6 up, then another 6 up, 12. All right, let's go have a look at the function again. So it's cosine function. Cosine starts high, okay, and then dips down. Right, so there's basically one cycle of the function. Right, so we presume that for whatever reason you get up onto the ride, up really high. Okay, so you climb maybe a ladder up to the top of the ride. I don't know, the ride drops down, touch the ground, bounce back up again or something like that, or go round in a circle. So you'd board the ride up at the top and then you would go around in a circle or something like that. Okay, so there we go. Make sure you go through the point there. I'm not going to fix that on mine, but please make sure that your notes have you going through that point. All right, so from this point on, it starts, then it goes down to here, to here, to here, to here, to here, to here. So what it obviously does is lets you off at ground level. Start up high, let off at the ground, go on your merry way. This is x of t versus t. All key features need to be labelled, so turning points. So I'm going to label a few of them, and if you can do that yourself, that would be fantastic. So this is 24, 0. This is 0, 12. This one here is 36, 48, 12, etc., etc. Each of them will fall into that pattern. For what values of t during the first 60 seconds of the ride is the height at most 3 meters? All right, so here's 6, here's 3. So when is it at most 3 meters? For what values of t during the first 60 seconds of the ride? So that is going to be 24, 36, 48, 60. So again, having the graph on this means that I know exactly which part we're talking about. So is at most 3 meters. Okay, so the highest it can be is 3 meters. So it's actually during this section here. This is where it's going to happen, between here and here. Okay, so we're going to get an interval between those two values. So what I'm going to do is solve it. So I'm going to say that 3 equals the function, which is 6 cosine pi t over 24 plus 6. All right, now what we're going to do is say that this is negative 3 over 6 equals cosine pi t over 24. Right, notice that this just happens to be a half, girls. Happens to be an exact value. All right, so what we can do is think about this as a base angle and a unit circle. So cosine is a half at, when is it? It is pi on 3, and we want negative a half. So it's going to be there at 2 pi on 3 is going to be a half, and over here, which is 4 pi on 3. So we're going to say pi t over 24 equals 2 pi on 3 and 4 pi on 3. Now note, I'm only going to give two solutions because that's when the height is at most 3 meters, between this value here and this value here, for the first 60 seconds of the ride. Then it's more than 3 meters at those other times. So again, having the graph allows me to know exactly how many solutions to generate. All right, so t equals, and so what we're going to do is 2 pi on 3 divided by pi on 24 is the same as 24 over pi. They cancel out. That's 48 over 3 equals 48 over 3 equals 16. So that one there is 16, and t equals 4 pi on 3 times 24 over 3, over pi rather, cancel, cancel. That is going to be 80, 96 on 3, which is equal to 32. So 16 and 32. So what values of t during the first 60 seconds of the ride is the height at most? So that's when it is exactly 3, is 16 and 32. So we're going to say t is an element between at most 3 meters, which means we're accepting 3 meters. So it's 16 to 32. Between those two values, inclusive of those, the height's going to be at most 3 meters for the first 60 seconds. All right, let's jump on the calc and see if we can bang out a quick solve on that one. So solve 3 equals f of x for x, please. And can you look between 0 and 60. Now, less than or less than and equal to, I don't really care because I know it's between there. In fact, I can even shrink it down even further. I can go between 10 and 50 because I know from the graph that it occurs somewhere for there. So I'm not really worried about the less than or less than and equal to. 16 and 32, bang. All right, here's our second problem. And what I'm going to try and do is speed up this process just a smidge and do some of the legwork on the calculator, even though I think from memory, a lot of these examples come out with nice exact values. The height above the ground, x meters of a particle that is suspended by elastic from the ceiling at time t seconds after the particle is released can be modeled by this function. Okay, so height above the ground. So what I think happens is a particle that is suspended by elastic from the ceiling. So like this thing is at the ceiling and it might be sort of like dropped and then comes back and then comes down, whatever it is. Okay, so it's going to come back down and again produce this sort of circular function type scenario. How high is the particle when released? That's x of 0, which is going to be cosine of 0 is 1, 1.2. It's going to be 4.7. Let's get the calc to confirm that. Okay, what is the minimum height of the particle? So what is going to happen, it's going to be a cosine function starting at 4.7 and the particle is going to drop, okay, and that's the lowest point it's going to get to. And that's going to be the mean line, subtract the amplitude. So it's going to be 3.5, take away 1.2, which is 2.5, 2.3, okay. Again, to speed up the process, you could go and F max or F min rather on the calculator. So F min, please, for this expression. Now the problem is you've got to know kind of where that occurs. You've got to give it a start. And so to do that, you need to know roughly what the period is. I'm just going to have a guess here and say 3. See if it gets it for us. So the minimum value is, no, that's not far enough. Yeah, this is a good example of why F max is not good here because we haven't hit our minimum yet. What's our period? Our period is 2 pi over 1 over 3 which is equal to 6 pi. So that's one cycle is 6 pi or 24 roughly. So let's go back to the calc and fire in at 24. Minimum value is 2.3. Wow, see how slow that is? Like, that's slower with tech than it is to do by hand, okay? So there's evidence there that like calculators haven't improved everything. All right, how many seconds elapse between consecutive times that the particle is at the minimum height? All right, so what's going to happen is the particle is going to do that. So it's going to fall, rebound up, then fall again. And that's actually going to be the period, okay? So it's going to hit again at the period. So that's going to be 6 pi seconds, or roughly 6 threes are 24. Every 24 seconds, it's going to then return to the same position because it's going to go once around to get back to the minimum. Sketch the graph of x of t between 0 and 10, non-inclusive of the 10. Okay, our mean line was 3.5. So there it is there at 3.5. And we've got this 1.2, so 3.5. This is 4.5, here is 4.7. Here's 3.5, 2.5, 2.3. So 2.3 is somewhere down here. Okay, now some students put lines in to give you guidance. That's okay if you do it, but rub them out once you're done. These dotted lines here usually represent asymptotes. So it's good to get some ideas on where your maximums and minimums are going to occur, but you do really need to rub those out to make sure that someone doesn't think that they're asymptotic there. Okay, so now let's work out the scale. So it's going to be 6 pi on 4 is equal to 3 pi on 2. Okay, so 3 pi on 2, which is 6 pi on 4. Then we're going to go 3 pi, which is 9. Okay, so 3 pi is roughly 9. So it's going to start there at 0. There. It's going to hit 3 pi, which is 3 lots of 3.1, which is 9.3. It's going to start to return. Okay, and I don't know what the 10 is going to be. I need the calculator to help me out with that one. So that's going to be f of 10, and that's going to be 2.32. So what it's doing at 10, so I'm going to guess here that this is roughly 10 here. It's going to start returning back up again. So my function falls down, hits the turning point, returns back up, and because it's not included, I'm going to open circle it there and say that it is 10, comma, I wonder if that's an exact value, I doubt it. Like, you could write that in, but that's just the function. So they probably, state endpoints to 2 decimal places where, so absolutely decimal. So 2.32, got to put that turning point in there, which is at 3 pi, comma, 2.3, and our y-intercept, which is 0, 4.7. Label your axes, x of t versus t. So a bit of a long axis there. I anticipated this being a lot longer. Now make sure you go back and erase those dotted lines there if you have put them in. For what value of t does the height equal 2.9? So here is 3, so we're there. Now, I don't know whether this one here refers to this information here, which is between 0 to 10, or it refers to when does it actually happen indefinitely, okay? So what we're going to do is jump on the calc and solve this and see where the question might be heading. So 2.9 equals, what's the function again? 1.2 cosine t on 3 plus 3.5. So I wonder whether that will generate an exact value. It does. Look at that. Cheeky. All right, so if we remove 3.5 from 2.6, we're going to get negative 0.6 over 1.2 cosine t on 3. This is cosine t on 3 equals, now times that by 10, times that by 10, and it's negative 6 on 12, which is negative a half. Okay, so what we're going to do here is produce a general solution for this one here. All right, how are we going to do it? So cosine t on 3 equals negative a half. When's that going to happen? It's going to be here at 2 pi on 3 and 4 pi on 3. So we're going to say that these are the two situations where we get negative a half. So we're going to go t on 3 equals 2 pi on 3 plus the period for cosine, which is 2 pi n. All right. Now what we're going to do is multiply this solution by 3 to solve for t. So t equals 2 pi. So multiplying by 3 cancels out that 3. And the period also changes. So we're going to do plus 6 pi n. Okay. Now let's do the other one. T on 3 equals 4 pi on 3 plus 2 pi n. T equals 12, that's 4 pi plus 2 pi n. Oop, no, 6 pi n. Okay, now that's interesting. Okay, so what we're noting here is that after the dilation from the y-axis, we're going to have solutions starting at 2 pi and then adding 6 pi to that, okay, and then 4 pi. So I think these solutions can be rolled into the one solution. So let's go a solve on that. 2.9 equals f of x for x. Okay, so 6 pi n, take 2 pi, 6 pi n plus 2 pi. Okay, so we're correct on that, but I think we can roll those into one solution. I'm just going to leave it as the two solutions and say where n is an element of z. Okay. Now, why would we consider combining them? Well, if you think about it, like if I put n equals 1, it's going to be 8 pi. If I put n is equal to 1, it's going to be 10 pi. Will I be able to generate? So you're watching me think this through, girls, and that's okay. So I've got 8 pi there as a possible solution. Is there another way to generate that? No, I think we're just going to keep them at two solutions. All right, and is this the last example? No, we've got one more. Okay, water leaks from a container through a hole that grows in size as a result of the pressure exerted by the water on the edges of the hole. The volume, V litres of water that has leaked out after T seconds of the hole first formed is modelled by this. The container initially holds 40 litres and the model is valid while the container holds some water. Okay, so find the value of B, the value beyond which the model is no longer valid. Okay, so this is a tan function. 3 tan Okay, so the way we're going to think about this one is the basic tan function will kind of go like that. Okay. Now, what we're going to do is essentially work out when it hits 40 for this function here, and that'll indicate that all of the water has leaked out. So what we want to know is when V of t is going to equal 40. Okay, so we're going to go ahead and solve this for t. So define our function. Okay, now the hard part. So what I've got to do is kind of give it a period. Okay, so I want to know when that's going to happen. That's the first positive value that I'm after here. Okay, so in looking at the period, the standard period of tan is pi. The n value here is pi on 36. So 36 will be one cycle. So I know that that is going to be 18 and negative 18 to give me 36. So it's going to be after, or one cycle of tan is going to be 18. So that 40 is going to be happening somewhere between 0 and 18. So let's find out. 0, x, 18. All right. Probably need another bracket in there. No, I didn't. All right, so t is equal to 17.14, i.e. after 17.14 seconds, V of t is going to equal 40, i.e. all of the 40 litres of water has leaked out. Find the volume in litres which is leaked out 12 seconds after the hole first formed. So what's happened here is we're going to go and jam in 12, and that value there will be the amount of water. So we're just going to go f of 12, and we get that. There's no decimal recommendation on that. There you go. So we're going to do v of 12 equals 3 root 3. So that problem there is easily doable without the calculator. So try that yourself. So V of 12 is 3 root 3 litres has leaked out. Use calculus to find the rate at which the volume is leaking out. Volume leaking out is increasing. Use calculus to find the rate at which the volume leaking out is increasing when T is equal to 6. Okay, so to do that, what we're going to do is we've got our function here, f of x. Right, so we'll just diff that function. Okay, which there's our derivative function. Now what we're going to do with our derivative is put in x equals 6 or t equals 6 to find out our rate. All right, so the way we're going to do it is I'm not going to show any working out for this one. We'll save that for a bit later and pretend that this is worth 1 mark. And I'm going to say v-6 is equal to pi on 9 litres per seconds. So pi on 9 litres per second is the rate at t equals 6. All right, last question. This has taken a little while. Concentration C units of a drug in the bloodstream T hours after taking the drug can be modelled by this. The model is valid until all of the drug has been absorbed from the bloodstream. Okay, so again, let's go define f of x equals 0.4, take away 0.4 times cosine 0. Okay, find the time in hours after taking the drug in which C is at a maximum. So what's going to happen here? Let's just anticipate it. So at our mean line is at 0.4. Our amplitude is that. Typical cosine will go down. This one is negative, so it's going to go up to the mean line, curve, and then come back down. Okay. So find the time in hours after taking the drug where it's at its maximum. So that's going to be there. So what I'm going to do is work out the period, which is 2 pi over pi on 4, which is equal to 8. The maximum will be here at this point here. So if the period is 8, the max will occur at 4. So when t is equal to 4. The time in hours is 4 hours. Find the maximum value of C. That's going to be C of 4. This is probably an exact value, but just need to speed this video up a bit. 4/5. Okay, so that could be obtained by hand. So it could be in an exam one. The drug is ineffective when it's less than 0.2 units. So from the graph, there would be 0.2 units, which is there. So it's going to be that part there and that part there. So how long does it take to become ineffective? Well, the drug is taken, initially it's ineffective. So how long does it take to become ineffective? It's initially ineffective, okay, but then it becomes effective between there, and now it's ineffective again. So what we're going to do is go over calc and solve. F of x equals 0.24x, and I'm going to go hunting between 0 and 8. Okay, so how long does it take to become ineffective? Well, we're going to assume by the wording of the question that it's assuming that initially, this initial stage, we're going to ignore it, and we're going to say that I've taken the drug and I want to know when it's going to be ineffective at the end. That's how I'm interpreting this. How long does it take to become ineffective? So we're going to say that it becomes ineffective when it's less than 2 units. So we're going to say when t is an element between 20 on 3 and 8, inclusive of that. All right, so we're going to say that this is the section here where it falls below 0.2 units. Right, how long does it remain effective? Well, it's between these two values. T is an element, and we're going to include them 4 on 3, 20 on 3. Okay, so that's what we're going to say. So it's these values of T. How long does it take to become ineffective? It's those ones there. Now, what we can do now is interpret those a little bit more so that we can talk about it in hours. So let's go with 20 on 3 first of all. And note that that's 6 2/3 hours. So after 6 hours and 2/3 of an hour is 40 minutes. 6 hours and 40 minutes. So that's when the drug is ineffective, after 6 hours and 40 minutes. But that precludes me talking about when it's ineffective in the first place, like I'm waiting for the drug to be absorbed into the bloodstream. All right, now this one here, when is it effective? It's going to be effective between 1 1/3 after 1 hour and 1/3 is and 20 minutes. So after 1 hour and 20 minutes, or not after, but at 1 hour and 20 minutes until 6 hours and 40 minutes. Okay, and that takes care of the includes. All right, so there's four pretty good modeling problems as well as the rest of these ones in the book.